Good afternoon, everyone. I'm Alan Jackson. I'm a professor of physics at Central Michigan University. I'm also chair-elect to the Division of Computational Physics, or DCOM. This is a DCOM-sponsored session, and the last talk in this session is actually an award talk. It's my honor today to introduce to you this year's recipient of the Metropolis Award for outstanding doctoral computational physics, recognizing research of outstanding quality and achievement. The award also underscores the importance of effective and moral communication of research results. This year's Metropolis Award recipient is Dr. Sean Kavanaugh. Sean, I looked up online, tried to learn something about him, but I learned that he's sort of a human example of entanglement, having worked in two groups, I guess, with David Scanlon at University College London and Aaron Walsh at Imperial College London. And for all the digging that I did, I couldn't figure out which institution actually gave you your PhD.
UCL Tech.
No,
Yeah.
UCL. Perfect. The citation award means for developing computational techniques and open source toolkits for the study of defects in solids and their application of electron hole recombination processes in semiconductor materials. Sean, congratulations on receiving this important award. Thank you very much.
Okay, good to go. Okay, great. So thank you. Firstly, thanks very much for the introduction. I think this is the longest introduction I've had for a talk so far, so I must be doing something right. And of course, I'd like to thank the organisers for inviting me and giving me this opportunity to speak about my research today. I also appreciate you all for sticking it out till the end today and showing up for this talk, which today is going to be about modelling the energy surfaces of defects in solids. Okay, so in this talk, time permitting, I'm going to discuss some of my work looking at defect metastabilities and then some global optimization strategies to handle this issue, before looking at some relevant case studies and finally a preview of some of my recent work looking at using machine learned potentials to accelerate defect modeling. Okay, so I'm going to start by giving the short story about how I ended up becoming interested in the energy surfaces of defects. So it all started many years ago when I was a young and fresh-faced first-year PhD student, and the focus of my PhD thesis was intended to be cadmium telluride. So this leading thin-film solar cell technology, but that still has an efficiency, so around 22%, which is limited by defects, and in particular, defect-mediated electron hole recombination. So the goal of my PhD was to leverage recent advances in compute power and methodologies, so theories developed by Audia Selkauskas and Lin-Wan Wang for directly computing non-radiative electron hole recombination, and to then see if we could answer some questions involving these defects in cadmium telluride. In particular, making use of recently developed computational packages, such as carrier capture, which was developed in one of the groups of my PhD, and also non-rad, so that was developed by Mark, our previous speaker, for directly computing these recombination rates. So using the popular supercell approach for computing the formation energies of defects, along with some early versions of some defect modeling codes that I've developed, I computed the formation energies of all intrinsic point defects in cadmium telluride, using hybrid density functional theory, including spin-orbit coupling. So what we find here is that, if I zoom in on the typical growth conditions of this material, we see that cadmium vacancies are the dominant defect species in this case. And they also show these multiple stable charge states within the bandgap corresponding to these energy levels for the defect within the bandgap, and thus the possibility to contribute to charge carrier recombination. So in short, this is because the energy levels associated with these defect charge transitions can act to capture electrons and holes from the band edges of our semiconductor. So if a defect level like this can sequentially capture an electron and then a hole, or vice versa, then this will give us a charge carrier recombination cycle, or essentially the annihilation of our electron hole pairs. In cases where a defect concentration is very low, such as in silicon or gallium arsenide, for example, or cases where the charge capture rates themselves are very slow, such as in halide perovskites, then the overall rate of electron hole annihilation or recombination will be very slow and thus have minimal impact on device performance. On the other hand, if we have fast overall rates of non-radiative recombination, annihilating our electron hole pairs before they can be extracted, this will greatly reduce the quantum or radiative efficiency, or in this case the extracted electricity, and thus be very detrimental to device performance. So I won't go into too much detail about how exactly these calculations are performed, but it's related actually to the phonon emission that Mark was talking about. But essentially it involves mapping out the potential energy surface between the defect in the two different charge states associated with this defect level or the charge transition, from which we can determine the energy barriers to this transition, so the delta E here, as well as the vibrational overlap factors, so essentially Frank-Condon type factors, and electron-phonon coupling coefficients, all of which enter our final rate equation. That said, for the most part, it is primarily these energy barriers which dictate the overall rate of these transitions in essentially an activated type process. So in this case, we find that we have quite a small energy barrier here to electron capture, so going from the neutral charge state to the -1 charge state, but on the other hand, quite a large barrier to hole capture, so going from the -1 charge state to the neutral state. So this gives us this picture where while we have fast electron capture, we have very slow hole capture, and so this will be the rate limiting step in our recombination process, and thus giving slow recombination rates. However, if we account for the fact that we actually have this low-lying metastable state for our neutral cadmium vacancies, just slightly higher in energy, where we have this metastable bipolaron state, and calculate its charge capture rates, we find essentially opposite behavior, where now we have fast hole capture but slow electron capture, and so it also would not give rise to fast recombination. But if we then account for the possibility of transitioning from this metastable state into the ground state, which we can do with transition state theory, so using the nudge elastic band method to calculate the energy profile for this transition and then estimating this transition rate, we find that it occurs sufficiently fast as to open up this rapid recombination cycle, where we go from -1 charge vacancies into the metastable neutral bipolaron state, which relaxes down to the ground state, and then back to the -1 charge state. So overall, we find that due to the presence of this low energy metastable state for cadmium vacancies, a fast recombination cycle is opened up. If we account for this in a full kinetic model of our solar cell under illumination, we find that this recombination process occurs sufficiently fast as to give a 5% reduction in the efficiency of this material, down from the 32% theoretical limit. And these calculations therefore reveal that cadmium vacancies, which were previously thought to be a benign defect species in this material due to the misidentification of the ground and metastable states for cadmium vacancies, are in fact crucial to avoid in this material, as well as rationalizing some of the observed behavior for this material as well. So the issue, however, is that neither of these two defect states, which combined give rise to this rapid recombination cycle, are identified with a conventional unperturbed supercell relaxation, which instead returns this higher energy tetrahedral state, which is actually benign for recombination. So of course, this is due to the fact that often the initial state of our supercell structure and thus gradient relaxation can lie closer to a local minimum on the potential energy surface, giving rise to this higher energy metastable state, which may not reflect the true defect behavior. If we remind ourselves that defect concentrations and thus their impact on material properties are exponentially dependent on the formation enthalpy, as this plot here illustrates, we can see that even relatively small changes in the formation enthalpy can yield quite large changes in the resulting or predicted concentration. More generally, we should remind ourselves that defect geometries determine essentially all properties and behavior of the defect. So formation energies, as we said, which dictates concentrations, doping, thermodynamics and more, but also localization, so whether the defect presents a deep or shallow level, recombination activity as we just saw, migration, catalytic activity and more. So making the identification of this behavior crucial. So, of course, we're not the first to notice this behavior and the importance of defect metastabilities in global optimization. And so listed here are some further examples of where this behavior had been noted and found to be important to defect properties. And typically it was identified either serendipitously or through manual searching. And of course, this isn't just an issue for defects, but can be an issue for bulk crystal structure optimization as well. However, typically we have experimental databases which provide us with a good initial guess of the material structure, such that a gradient optimization will typically find the global minimum. For unknown crystal structure prediction, however, this is a huge avenue of research and many different methods have been proposed. But the thing is, defects are unknown structures. We have no database of known defect structures yet, and so efficient structure searching techniques are required. So with that in mind, I had the goal of developing a method that was both accurate and efficient in navigating the defect configurational landscape and identifying ground state and metastable defect structures. So in particular, I had the idea to leverage the localized or so-called molecule in the solid type behavior of defects in materials, where the key interactions are primarily with the nearest and next nearest neighbors around the defects, as well as the fact that the reconstructions we tend to see around defects, or the changes in their structure, are typically driven by the need to accommodate the excess charge associated with that defect species. So what I mean by this is that if we take a cadmium vacancy, for example, in the fully ionized charge state, where we've just removed the cadmium ion, we have the -2 charge state, in which case there is no excess holes or charge to localize. But in the neutral charge state, we now have 2 excess holes present, and so typically this will result in a reconstruction that involves movement of 2 of the defect neighbors. So in that case, we had the 2 atoms coming together to form a tellurium dimer in the ground state, or the 2 atoms moving apart to form this metastable bipolaron. So with this logic guiding us in terms of which bonds to distort, we create a mesh of trial distorted structures. And so this isn't always perfect, but it typically points us in a good enough direction or along the likely reconstruction paths, such that rattling and relaxation will find the ground states. And so with this mesh of trial distorted structures, we then finally rattle those structures, meaning we add some small constrained random displacements to break symmetry and disrupt the long-range lattice potential. So we then relax these structures at a cheap but reliable level of theory using cheap coarse numerical parameters, which makes the calculations run fast while retaining sufficient qualitative accuracy so as to identify distinct defect structures. If we then go on and plot the energies versus distortion, we see that our defect ground state is obtained for a certain distortion range. So these points here in this case corresponding to these points in the potential energy surface, where our bond distortions have been sufficient so to push over this local minimum and identify the ground state defect geometry. So in summary, the strategy here is to use a coarse exploration of the potential energy surface to identify the ground state and metastable defect structures before continuing with the final converged energy calculations. We found this method to be surprisingly successful at identifying these reconstructions of defects in solids and reproducing all known cases of this behavior in our benchmark dataset. By then going on and applying this method to a wide and diverse range of materials and their defects, we saw a widespread prevalence of this behavior, finding it to occur in many cases that had not been previously realized. And in fact, from this study and the studies that have come since using Shaker-Mark, we've actually found this behavior for defects in every material that we've looked at, where you find these energy-lowering reconstructions that are missed by the standard defect modeling procedure I described earlier. So this method has now been used in a wide variety of different defect studies, looking at defect behavior across a range of materials and applications, some of which I've been involved in. And so here I give a select few examples to just give a flavor of these cases. So this has included the formation of molecular oxygen in nickel-rich cathode materials, which is key to their degradation processes, as well as oxygen vacancy reconstructions in strontium titanate, which is key to its photocatalytic performance. We've also used it to look at polarons in this emerging solar cell material, copper antimony selenide, as well as charge compensation in transparent conducting oxides, some other emerging solar cell technologies, and it's also been used to look at quantum computing sensors in some other materials. So digging into the reconstructions we tend to observe across our initial test set and the studies that have followed across a wide range of material space, some of the most common distortion or reconstruction motifs we tend to see are shown here. So firstly, dimerization, like we saw with the cadmium vacancy, where you have this kind of small barrier, but once it's overcome, a strong dimer type bond, which lowers the energy of the defect. You also have cation-anion rebonding, so you have some sort of rearrangement to give rise to more favorable cation-anion bonds. In other cases, it can be put down to Jahn-Teller effects, so symmetry breaking and electronic structure. And in other cases, it's electrostatically driven, so some rearrangement which lowers the electrostatic energy of your system. Okay, so in the next section, I want to briefly discuss some case studies where defect structure searching with shake and break has revealed some key insights and bigger takeaways for the behavior of defects in solids. So earlier I mentioned electron hole recombination, which is one of the key mechanisms through which defects affect performance in optoelectronic materials. So solar cells, but also photocatalysts, LEDs, single photon emitters, and more. So I said that our simple conventional picture of recombination at defects is where we have this one defect level like this, and then two charge capture processes which give rise to a recombination cycle. As we saw in the cadmium vacancy case, however, we can actually have alternative accelerated pathways involving metastable states, such as this case where we first capture into a metastable defect state before relaxing back to the ground state, then capturing back to our original charge state. So these findings really piqued my curiosity, as they showed that our conventional simple picture of just a single defect level for electron hole recombination at defects may not be complete in many cases. So in reality, we can have multiple metastable states present for our various different defect charge states, where the overall capture and recombination rates will be governed by the sum of these various transitions. So in this work referenced here, I took a wider view of these potential possibilities for defect-mediated recombination in semiconductors and insulators, finding firstly the tellurium interstitial in cadmium telluride to be an interesting exemplar of this behavior, where due to the presence of this very low-lying metastable state, we can actually thermally excite into this metastable state before having a fast capture transition and then back to our original charge state. So in general, our analysis suggests that these metastable states will often act as catalytic intermediates in these recombination cycles, as we saw for cadmium vacancies and here also for tellurium interstitials, by opening up alternative and often accelerated charge capture pathways. And so it's important to identify and include these metastable states when modeling recombination processes. With the adoption of shake and break and other defect structure searching approaches to reveal the extent of metastabilities at defects, we're left with the conclusion that, in general, it is likely that these metastable states are far more present and important to recombination processes than has been previously realized. I would also like to mention that beyond defects and polarons, shake and break has been successfully used to identify similar energy-lowering reconstructions for other localized species. One example is self-trapped excitons in these vacancy-ordered perovskites, where high thermal sensitivity of emission lifetimes has been used to facilitate their application as ultrasensitive remote thermal imagers. So this behavior had been identified experimentally in some high-profile papers, but the underlying mechanism couldn't be explained by theory until shake and break revealed the presence of this lower energy exciton geometry with this very small barrier to that transition, rationalizing the high thermal sensitivity of our emissive state here. Some other key examples where shake and break has revealed some general trends is the strong ability of anions, in particular halogens, chalcogens, and oxygen, to form dimer and trimer type motifs at defect sites in order to satisfy dangling bonds and annihilate excess holes. So we see this here in the case of antimony selenide, where these dimer type motifs have greatly lowered the energy of our vacancies and give rise to this unusual 4-electron negative U behavior, as well as in a wide gap oxide, so candidate TCO here, where it lowers one of the vacancy energies by nearly 4 electron volts. So shake and break has since revealed this behavior, mostly but not only vacancies, in well over 50 materials at this point. Okay, so in the final section of my talk today, I'm going to talk about some of my ongoing work in the realm of machine-learned interatomic potentials. So to motivate this section, I will state the obvious and say that defect calculations are expensive. This is a result of the requirement for large simulation supercells, high levels of theory, and many calculations in order to achieve the requisite accuracy. On top of that, we see the importance of these additional steps of structure searching, though I will say that this usually amounts to only around 10 to 20% of additional computational cost when using reasonable coarse relaxation parameters as recommended with the shake and break approach. Ideally, however, we would like to be much more comprehensive with this step, particularly when it comes to low symmetry systems, which may have many locally stable minima. So overall, this results in our defect simulations being expensive, slow, and somewhat limited in scope, where often we have to try and hone in on specific defect configurations, which we believe are important and relevant to experiment, but maybe missing out on the overall system behavior. So the thing is, we have the tools to do all these calculations, and now in a semi-automated fashion, which is capable of handling large amounts of calculations and data. So as I mentioned, we have the associated theories and packages to explicitly compute, for instance, carrier recombination processes. So I mentioned carrier capture and non-rad, and there's others, as well as, of course, migration pathways, thermodynamics, etc. And one such toolkit I'd like to briefly mention here is the comprehensive defect simulation package called DOPED that I developed during the course of my PhD. So here it provides a robust platform to manage the full defect simulation workflow, from efficiently generate possible defect configurations and their associated input files, through to parsing and analysis, where, for instance, it'll automatically compute finite size corrections, eigenvalue analysis, and all the way through to more complex thermodynamic analyses. So we've worked hard to put together a comprehensive documentation site, shown here, with many tutorials, and it's now been used in over 30 different defect studies, so please have a look at this if you're interested. But the point is, we now have the theories and the tools to expand the scope of our defect investigations to improve our predictive accuracy, but the issue is simply that the underlying quantum mechanical calculations are so expensive that they still limit this process. So that brings me to machine-learned interatomic potentials. So these are machine learning models that are trained on data sets of quantum mechanical calculations, and with sufficient input data can then accurately reproduce the energies and forces from these quantum mechanical simulations without a fraction of the computational cost. These methods can then be used to analyze and predict atomic behavior at longer and wider timescales than is possible with conventional methods when used appropriately. So there are a lot of issues with trying to use machine-learned interatomic potentials with defects, but if we could successfully implement them in this area, then it would allow us to greatly expand the scope of our investigations. So the issue of defect energy surface exploration, which I've been talking about today, is perhaps the most ideal use case of these machine-learned interatomic potentials for defects, as this step does not require as much quantitative accuracy as we do when looking at actual formation energies and concentrations, but rather just needs to be sufficiently qualitatively accurate as to identify candidate low-energy structures, which can then be checked with DFT. So one way that we've looked at doing this was my collaborator Aurea Mosquera-Louise taking the M3G-net interatomic potential and then retraining it on shake and break relaxations in a given chemical subspace, so in this case metal chalcogenides. Here we find that this model can predict energy lowering reconstructions for unseen defects in unseen compositions with a success rate of around 90%. While the energy differences themselves are not quantitatively reliable, the model seems to perform quite well in qualitatively identifying distinct defect structures, which can then be used to reduce our distortion sampling set down to maybe one or two pre-relaxed structures, which can then be computed at a reliable level of theory, such as hybrid DFT, to identify our ground state and metastable defects. So I think this is a promising initial sign that these machine learning force fields, particularly if optimized for defects, could help accelerate the pace of defect modeling. Okay, so in particular, I want to talk about a recent independent project I pursued in this space, looking at the behavior and prevalence of a unique type of stoichiometry conserving defect complex known as split vacancies. So these can be thought of as essentially a complex between an interstitial and two neighboring vacancies. Or if we think about going from the initial point vacancy or a simple vacancy, having the movement of an atom somewhat nearby into the interstitial space between its original lattice site and the vacancy site, and giving us this vacancy complex, so two vacancies with the interstitial in between. So these defects have been shown to be important in a handful of cases, such as for power electronics in gallium oxide, which was quite a big finding for this community, as well as in some work that I've been involved in looking at candidate transparent conducting oxides, in which case they limit the dopability of our material. However, they are actually incredibly difficult to identify. For instance, the only reason this defect here was identified in the case of gallium oxide was that in this work from 2011, Joel Varley wanted to look at the migration pathway of these vacancies. And when performing this calculation, found that the expected transition state of this migration pathway was in fact the ground state, being a good 1 electron volt lower in energy and having quite significant implications for the behavior of this defect. And this serendipitous identification of the defect reconstruction is typical of the previously known cases of this reconstruction behavior that inspired the development of shake and break. So while shake and break has miraculously revealed these split vacancies in 1 or 2 cases, in general it does not perform particularly well at identifying this specific type of defect. And that's because this reconstruction is somewhat unique in that it is what we would call a non-local reconstruction. So unlike typical defect reconstructions, which usually involve some movement of our nearest and next nearest neighbours to the defect site, this particular reconstruction involves movement of a defect which is initially very far away from the defect site. So in this case, the 10th nearest neighbour shell. And so we can see this from the figure here on the right, which plots the average maximum displacement of atoms relative to their bulk positions as a function of distance to the defect site, where we see that, well, firstly for normal, simple vacancies, we have the typical exponential-like tail-off as we move away, but for split vacancies, we have this peak at around 3 to 5 angstroms. So I wanted to dig deeper into this type of defect. There have only been a handful of observed cases of this specific type of defect in materials, but again, there's a question of whether this is due to an inherent rarity in nature, or simply that they are hard to identify and we haven't had methods capable of identifying them previously. So what I find, firstly, is that the underlying energetics of these states are actually quite simple, involving mostly just electrostatics and strain. So this is corroborated by the fact that, well, firstly, these types of defects have mostly been identified for fully ionized defect charge states, which I said is where we think about just taking the ion out of our material. And so that would be like a -3 charged gallium vacancy for the +3 cation, +3 gallium cation and gallium oxide, or a -1 charged lithium vacancy, etc. And so in these defect states, we have no excess charge to localize, and so these are typically the most simple of defects, where it is mostly electrostatics and strain effects which govern their behavior with minimal covalent contributions. So if I take this simple electrostatic energy model and then enumerate all possible split vacancy configurations in the set of known materials where this behavior occurs, I find that in those which give lower energy structures when relaxed with DFT, which are the ones marked in with X's here, are in most cases at the low energy range of these electrostatic energies. So they are not always the absolute lowest electrostatic energy, but they are close enough that this makes it, this electrostatic screening, a very good but not perfect screening metric for this behavior. So using a test set of a few hundred stable metal oxides and generating all possible interstitial divacancy combinations, in other words, split vacancies, with some reasonable distance constraints, gives nearly 200,000 candidate split vacancy geometries. If I then use this electrostatic screening model and reduce this to only those with electrostatic energies comparable to that of the simple point vacancy, this reduces to around 4,000 low energy candidates, which then relaxed with DFT show that in 10% of all cation vacancies in this data set, we have a lower energy split vacancy geometry, which has an energy going from 0 to -3 electron volts lower energy than the related simple vacancy. So on the right, I show the distribution plot of these energies relative to the simple vacancy, where we see firstly that as the oxidation state increases, so essentially our system becomes more charged and where ionic bonding dominates more, the electrostatic or the final energy gain of this split vacancy state becomes even more significant. So here I find that the electrostatic model does quite a good job of screening to reduce the search space of these candidate split vacancies, but on its own is still not a sufficiently good metric as to actually predict the final relative energies of these split versus isolated vacancies. So taking advantage of the fact that while they come with this enormous configuration space to search through of possible split vacancy geometries, the underlying energetics of these defects are actually quite simple, mostly involving electrostatics and strain effects with minimal covalent bonding and no charge localization. And so this suggests that machine learning interatomic potentials, which are trained on large DFT datasets, could be sufficient so as to actually predict their formation. So taking my DFT calculated test set that I just discussed there, and then evaluating the potential with some popular machine learning interatomic potential approaches, I find that a standard model can successfully predict the energetic preference for simple versus split vacancies in 90% of cases. Accounting for the fact that the prevalence rate of these lower energy split vacancies is around 10%. This gives us a true positive hit rate of just over 50%, with a false positive rate of 1% and a true negative rate of 99%. So if I take a more exhaustive approach, where I consider all machine learning predicted split vacancies with energies within 0.35 electron volts of the simple vacancy as candidates, this then increases to a true positive rate of 80%, but with a false positive rate, or true negative rate of 90%. So overall, these numbers correspond to a reduction of over 2 orders of magnitude in the number of DFT calculations that we'd need to do to identify these split vacancies in the electrostatically pre-screened subset, which itself is already about a 2 orders of magnitude reduction from the set of all possible split vacancy geometries. Just one other point to mention here, that is that I've tried both the NQUIP and the MACE interatomic potential for this task, which thus far have achieved similar accuracies, with the with the NQUIP potential being about twice as fast due to some recent infrastructural developments, which my colleague Chunwei will be talking about on Wednesday. So I wanted to go bigger and see if I could demonstrate the presence of these defect states across an even wider range of material space, leveraging this drastic machine learning acceleration. So this allowed me to screen all known crystalline inorganic solids, so those listed in the ICSD, as well as predicted metastable materials on the Materials Project database, which together is around 150,000 inorganic solids. So with the geometric and electrostatic screening procedure that I've implemented and doped and described earlier, this gives around 200 million candidate split vacancies based just on geometry, which is then reduced to around 1 million candidate low energy split vacancies using the simple electrostatic screening. Putting this through the machine learning foundation model approach that I just described, it gives out tens of thousands of lower energy split vacancies across a wide variety of material classes, with energy differences up to several electron volts, as we saw before, as compared to the around 10 previously known cases of this behavior. So looking at correlating properties with the prevalence of these energy-low reconstructions, the clearest trend I find is with the point group symmetry of the cation site. With higher symmetry sites, as quantified by the point group order here, or essentially the number of symmetry operations, giving rise to a higher prevalence of split vacancies, or split vacancies where they are lower energy than the simple point vacancy. And this is likely related to the fact that vacancies at these higher symmetry sites correspond to greater amounts of unfavorable dangling bonds and electrostatic energy loss, and so split vacancy formation is more likely to reduce the electrostatic energy relative to our simple vacancy in these cases. Okay, so some key takeaways here are that there are in fact many more split vacancies than are previously known in inorganic crystalline solids, and that these are a much more common motif for vacancies than previously realized. I think this is a nice early demonstration of the potential utility of machine learned foundation models, but should be taken with some very important caveats regarding their use. Namely, in this case, the only reason they work so well is that we have this combination of very simple underlying energetics, so just mainly electrostatics and strain, but with this enormous configuration space to search through. For the other types of reconstructions we often see at defects, typically involving some form of charge localization, I know from testing these methods they in fact perform terribly for these cases. So I think this highlights that these machine learning models can be incredibly useful when used intelligently and in the right context, and terrible when not. So as a final summary, I'd like to highlight some key takeaways from these works. We've seen that defect energy surfaces can be more complicated than previously thought, requiring global optimization strategies such as shake and break and others to ensure accurate and robust predictions. We saw that with charge carrier recombination, recent work in the field has meant that we can now directly and accurately model these recombination processes. However, we've also seen that defect metastability can be surprisingly important for these processes, and again demonstrating the importance of defect structure searching and consideration of metastabilities. Lastly, I talked about this recent machine learning potential studies on reconstructions and defects, which I think is a highly promising demonstration of their potential utility in this area, but also coming with some important caveats. Okay, so to wrap up, I'd like to thank my advisors that I've had along the course of these studies, which have been Professors David Scanlon and Aaron Walsh for my PhD, and Professor Boris Kaczynski for my fellowship. I'm continuing my research in this area, so if you are interested in any way, please do reach out to me. And so with that, thank you very much for your attention.
Thanks for a very nice talk. Have you thought about applying shake and break to study the structure of dislocation cores?
That's a great question. We've thought quite a bit about that. I know some people have already started to look at using some of these global optimization strategies for defects. So I know Stefan Lani, I believe, has used, I'm going to forget the name of it, but it's KLM, I think, to look at them. And so they're a case where I think people had thought about this problem a bit more generally before. But in general, I guess shake and break is definitely built around point defects. And so there would be a few modifications we need to use in those cases. So in particular, we use this idea of the excess charge of the defect species to try and dictate which bonds to distort. So we could just apply, I guess, with applying similar bond distortions across the dislocation, but I think we'd need to be smarter, maybe building in some consideration of symmetry. But yeah, so it's something we've thought about but not actually worked on yet. Thank you.
Thank you very much for the great presentation. So I'm curious, for using machine learning potential for predicting defects, do you see any trends between different category of defects? Which category is harder to predict? For example, between shallow and deep, between charged and neutral? Do you have any?
Yeah, great question. So definitely for the first part, between shallow and deep, they're definitely much better, I would say, I guess, for what we would usually call shallow defects. I guess that can be debated, but so like, for example, in this case, I looked at the fully ionized charge states, where we've just taken out the ion, and because they're much more simple, with just electrostatics and strain involved, machine learning potentials do a lot better. But then in other cases, if you have a deep defect that involves some form of charge localization, typically the models are quite poor for that. And most of that, it seems, is likely just due to the fact that most of these machine learning potentials are also trained on semi-local DFT data. And so maybe if we had a database of hybrid DFT for defects, it could be much better, but of course that's going to be very hard to build. And then the second, when you said, okay, you said some charge states, right? Yeah. So I think, in general, it'd be better for fully ionized charge states, and for neutral charge states, not as good, I think, in most cases where you have this, this charge localization at play.
Thank you.
Yeah.
Hey, Sean. Hi. Thanks for the nice talk. Your example of the metastable states made me wonder something. You showed how a metastable state can enhance recombination, but could the opposite be true, that a metastable state holds on to the charge long enough and slows down recombination?
Yeah, that's a great question, and that's something we thought about as well at that point. I think the conclusion we came to is that, it definitely can reduce the recombination rate, but the effect should be much less significant than the potential acceleration. So the way, I guess, it could reduce the recombination rate is in the case you said, where it takes some population of the charge state, which then is inactive for recombination. But the typical, if it was metastable, it still is higher in energy, and so I think you're maximizing it around maybe like a 50% population loss, or like a factor of 2 maybe reduction in the recombination rate relative to the initial ground state, whereas I guess the acceleration can be many orders of magnitude faster due to the nature of charge capture rates. So I think that was kind of our general conclusion.
So for your charge transfer process, do you consider the non-adiabatic nature? Is it like a Marcus theory-driven electron transfer process, or do you have is it all transition state theory?
Good question. Yeah, so it's related to Marcus theory. So I guess a lot of the methods and theories for it have built on Marcus theory, but it is the non-adiabatic approach. So in particular, I've used the one-dimensional configuration coordinate approach developed by Audrey Salkauskas. But there are other methods out there. So there's the approach of Lin Wan Wang I mentioned, where they instead compute essentially the phonon dispersions of the two different defects, and then use that together those kind of matrix elements to then predict the transition rates, but then typically that involves having to make these harmonic approximations. And so I guess the different methods that are out there at present involve one or other use of an approximation. But yeah, that's the one that we've mainly used. Thank you.